Hi students, today we are discussing the central limit theorem. This theorem is an important theorem in statistics, and it is mainly because of this that the normal distribution has gained so much importance in statistical theory. This theorem states that the sum of very large number of random variables is approximately normally distributed with the mean equal to sum of the means of the variables and variance equal to sum of the variances of the variables, provided the variables satisfy certain very general conditions. This theorem has been established under various sets of conditions. Because of this, we have various forms of central limit theorem, but we have to study only one, that is Limber-Levy form of central limit theorem. That Limber-Levy form of central limit theorem, there are some assumptions are here. That is, first assumption is the variables are independent. Here we are considering n random variables x1, x2, etc. xn. These variables are independent. Second condition, they are identically distributed. That means all the variables follow the same distribution. That means x1 follows n mu sigma square, x2 follows n mu sigma square, not n mu1 sigma 1 square, n mu2 sigma 2 square. x1 follows n mu sigma square, x2 follows n mu sigma square. That means in general we can write xi follows n mu sigma square for I equal to 1 to etc. n. That is, here we are considering xi's are independently and identically distributed random variables. We are in short we are getting, that is IID random variables. Then third condition is the mean and variance exist for all the random variables. And the fourth one is all the variables have same mean and same variance. These are the assumptions of Limber-Levy form of CLT. Okay, here the Limber-Levy form of central limit theorem. The statement is, if x1, x2, etc. xn are independently and identically distributed with the expectation of xi equal to mu and variance of xi equal to sigma square, and let us take Sn, the sum of these random variables x1 plus x2 plus etc. plus xn, then expectation. This also asymptotically normal with the sum. The mean is expectation of Sn is the sum of the means. Expectation of xi equal to mu, then Sn is mu plus etc. mu, that is n mu, and variance of Sn is sigma square plus etc. sigma square n sigma square. Then this is the theorem. That means if xi is at IID random variables and Sn is the sum of these random variables, then let us take Zn is, or Sn is normally asymptotically normal with mean n mu and variance n sigma square. Asymptotically normal means it tends to normal as n tends to infinity. Or we can write this as Sn minus n mu divided by root n sigma n follows n01 as n tends to infinity. Or we can say Zn is asymptotically normal, or it follows n01 as n tends to infinity. Okay, this is the standardized form of Sn. Sn minus its mean divided by standard deviation, that is root n sigma. Then the proof. This is the statement of the theorem. If xi's are IID random variables with mean mu and sigma's variance sigma square, let us take Sn is the sum of these random variables. Then Sn also follows asymptotically normal distribution with mean n mu and variance n sigma square. Or Zn is Sn minus n mu by root n sigma, that follows n01 as n tends to infinity. Okay, the proof. Let us consider the MGF of xi. Generally we are taking MGF, moment generating function, the definition of mxi. Mxit, we can write the definition is expectation of mxt is expectation of e raised to tx, or we can write here as expectation of e raised to txi. Then we have studied e raised to x is 1 plus x by 1 factorial plus x squared by 2 factorial plus etc. We can write e raised to x like this. Then if you are substituting here, what will we get? It is 1 plus txi by 1 factorial plus t square xi square by 2 factorial plus etc. If you are taking expectation for this, then expectation of 1 is expectation of a constant is constant itself, so it is 1, and here t by 1 factorial expectation of xi plus t square by 2 factorial into expectation of xi square plus etc. That is equal to 1 plus t by 1 factorial. What is expectation of xi? It is mean. We can denote it as mu1 dash plus t square by 2 factorial into mu2 dash plus etc. Where mu1 dash, mu2 dash etc. are the moments about 0 of xi. Okay, we have to show that Zn equal to Sn minus n mu by root n sigma follows n01 as n tends to infinity. As we have studied in binomial tends to normal, we have used the MGF technique. So, the same technique we are applying here also. So we are writing this. We have to show that m Zn t tends to the MGF of normal as n tends to infinity. So we are starting from here. M Zn t is equal to, we can write it is, Zn is Sn minus n mu by root n sigma of t, or we can write this as m Sn minus n mu of t by root n sigma, using the property of MGF. M a x t is, we can write it as mx of at. Here a is 1 by root n sigma, so t by root n sigma. It is in the denominator, so it comes here. Okay, then now this is of the form ax plus b. If it is in the form ax plus b, we can say this Sn contains xi, sum of xi's. So this is a random variable and this constant. So we can take it as, if it is m ax plus b of t, this is equal to e raised to bt into mx of at. So we can write this as e raised to minus n mu t, this by root n sigma into m Sn of t by root n sigma. This is equal to e raised to minus n mu t by root n sigma into m Sn is x1 plus x2 plus etc. plus xn of t by root n sigma. This is equal to e raised to minus n mu t by root n sigma into, we know that xi's are independent. So the product of sum of these is, we can write as product of MGF. That is mx plus yt is equal to, we know that mx plus yt equal to mxt into myt. So we can write this as product of I equal to 1 to n mxi of t by root n sigma. We can write this as, this is equal to e raised to, we can cancel this root n, so root n mu t divided by sigma into product of mxi t by root n sigma. Here xi's are identical random variables, identically distributed, that means all have the same MGF. So the product of this one, that means MGF here mx1t by root n sigma and mx2 t by root n sigma all have the same MGF. So we can write this as mxi of t by root n sigma the whole raised to n. That is equal to e raised to, here minus sign is here, e raised to minus root n mu t by sigma into, we have written here mxi t is equal to 1 plus t by 1 factorial into mu1 dash plus t square by 2 factorial into mu2 dash plus etc. We are substituting that here. Then it is mxi t is equal to this one. Here instead of t by root n sigma is here. So we are writing this is 1 plus t by root n sigma divided by 1 factorial into mu1 dash plus t by root n sigma whole square by 2 factorial into mu2 dash plus etc. all raised to n. This n. Then here e power, here the whole raised to n is here. So we are taking logarithm on both sides. Then it is log m zn t is equal to, here product of these logarithms we will get the sum. Then logarithm of e is minus root n mu t divided by sigma plus logarithm of a term raised to n is n times logarithm of this one. 1 plus, we can write this as t by root n sigma into mu1 dash plus t square by 2 factorial is 2 into root n is n sigma square into mu2 dash plus etc. Then we can write this as minus root n mu t divided by sigma plus these all steps we have done, the binomial tends to normal. The same case here, logarithm of 1 plus x, that is logarithm of 1 plus x is equal to x minus x square by 2 plus x cube by 3 minus etc. So here x is this part. So we can write this as t by root n sigma into mu1 dash plus t square by 2n sigma square into mu2 dash plus etc. This is the x minus t by root n sigma mu1 dash plus t square by 2n sigma square into mu2 dash plus etc. the whole square divided by 2 plus etc. Or we can write this as order of 1 by n raised to 3 by 2. What is this? This term denotes terms with the n raised to 3 by 2 or higher powers of n in the denominator. Here if we are putting n tends to infinity, the whole term vanish. That's why we are writing like this. Okay. Then we can write this as minus root n mu t divided by sigma plus next term is n into t by from this n into t by root n sigma into mu1 dash. N by root n is root n t by sigma into mu1 dash plus next term is n into t square by 2 n sigma square. This n will cancel, then t square by 2 sigma square into mu2 dash plus here the other terms are order of 1 by here root n, here n, the next term is n raised to 3 by 2 or n root n, and this n will cancel, then 1 by root n will be here. If you are substituting as n tends to infinity, the term will vanish. So we are writing order of 1 by n raised to 1 by 2 from here, and from this minus 1 by 2. If you are taking the square, what will come here? It is t square by n sigma square into mu1 dash square plus next term. This n here, that n is here, and this n. Okay, then n is common for all this. So n into minus 1 by 2, that is minus n by 2. Then taking the square a plus b plus c plus etc. the whole square, a square plus b square plus c square plus etc. plus 2ab plus like that. We are considering only the terms with the power. The denominator n raised to 3 by 2 up to dash. The other term will vanish if substitute as n tends to infinity. Then t square by n sigma square into mu 1 dash square plus next term will come t raised to 4 by 4n square. Then 4n square, if you are cancelling this n will be here, that term will vanish, so we are not writing that one. Then the next term will the higher powers of n in the denominator, so there is no need of writing that. Then next consider if it is a and this b, next term is 2ab will come, that is 2 times t into t square by root n sigma into 2n sigma square into mu 1 dash into mu 2 dash. Okay, here also if we are multiplying with this n will cancel, denominator root n will be here, so there is no way of writing the other terms, so we are writing the higher powers of 1 by n or 1 by 2 or 3 by 2. So here mu is here and here mu 1 dash is here. Here xi's are normally distributed with the mean mu. So this mu 1 dash is also mu. Mu 1 dash is the first row moment. Here xi's are normally distributed with the mean mu. So minus root n mu t by sigma, here root n mu t by sigma. This term will vanish. Then the next term is t square by 2 sigma square into mu 2 dash. Next consider this one. Here if you are multiplying this with n by 2, here n will cancel and t square by 2 sigma square into mu 1 dash square minus next term is this n will come, and so we are writing all as the higher power of 1 by n raised to 1 by 2. Then here we can write t square by 2 sigma square common, then mu 2 dash minus mu 1 dash square plus this term. Then as n tends to infinity, logarithm of m zn t is equal to t square by 2 sigma square of mu 2 dash minus mu 1 dash square is the variance mu 2. Mu 2 is, we know that mu 2 is sigma square plus this term will vanish, so sigma square cancel, this is t square by 2. Then m zn t is equal to e raised to t square by 2 as n tends to infinity, which is the MF of standard normal distribution. That means Zn follows as n01 as n tends to infinity, or we can write as Sn follows normal with the mean n mu and standard deviation root n sigma as n tends to infinity. This is the proof. Thank you.